for those who are following the course to pass the exam, there are subjects I won't cover with respect to the syllabus. For instance, in the end, I will not speak about Casimir effect. I will not have the time. And also renormalization, I won't touch. Today we will face the general tool, Bogolyubov's transformation, which is used after to the standard description of the Unruh effect and of the Hawking radiation. So today and the lecture on Monday, I don't know if there will be also Matteo present. Maybe he will tell us also about his own recent paper if he comes. So today and on Monday, Unruh effect and Hawking's radiation, and on Wednesday, de Sitter and anti-de Sitter in one lecture, maybe longer lecture. So the general topic of Bogolyubov transformation is, I would say, the standard tool in this context. As we remember, the general formalism is that we do have a Lorentzian manifold, which is globally hyperbolic for the moment. And these three things uniquely fix the commutator if you are studying the Klein-Gordon equation. So the commutator gives the algebra of the fields. Okay. Then you open a book in quantum field theory and curved space-time, and you are taught about the definition of the so-called Klein-Gordon product. And they ask you to find a complete set of solution of the Klein-Gordon equation that diagonalize the Klein-Gordon product. So let's call the set of solution, we label it by an index I, that it can be continuous or discrete. These are solution of the Klein-Gordon equation, and this is the definition of the Klein-Gordon product, which is indicated this way. And the recipe of canonical quantization starts by trying to find a basis. But the word basis here is a little bit misleading because we do not yet have a Hilbert space such that the functions are orthonormal with respect to this product. Their complex conjugate are anti-orthonormal. Let's say there is a minus here, and they are mutually orthogonal. This recipe, together with, so now you are going to write the field, the quantum field, this way as an expansion on the basis. And this recipe, as you see, there is no hat yet. So it's an algebraic recipe. Is something you have solved the Klein-Gordon equation in the field algebra, not yet realized in a Fock space. So if you compute the commutator, which is the thing which is uniquely fixed by the Lorentzian structure of the manifold, this has an expansion this way. So we can summarize the whole thing by saying that the canonical quantization procedure is a recipe to find the commutator. Okay, diagonalize the commutator, and you see this is an anti-symmetric writing in terms of the modes. What you call a mode, you call a solution of this equation, a family of solutions of this equation that satisfy these properties. Okay, these properties allow to you a unique answer. The commutator, which is written in a form of an expansion. Not always this is possible, I mean, practically speaking. But in principle, it is always possible to find the commutator C, because it's linked to the Lorentzian structure of the manifold. And then you remember that we said that quantizing the theory means representing it in a Hilbert space, means is equivalent to finding a positive definite two-point function satisfying this functional equation. It's a non-differential equation. And if you look at the structure of the commutator, there is an obvious solution at hand, which is this. And this is manifestly positive. Saying that this is the two-point function is totally equivalent to saying that the vacuum is annihilated by the destruction operator. It's the same thing. Okay? So this is the two-point function related to the basis you have constructed. Okay? But of course, you can start now playing around with these modes. You can now, and we enter in the subject of today's lectures, consider linear combination of such modes. Okay. In such a way that uj, ui star is these are perfectly well defined solution of the Klein-Gordon equation. Again. Okay. So you can impose canonicity of this basis. Okay. This means that you ask for a normalized Klein-Gordon product. Compute this thing. What is it, this thing? If you input this inside here, let's do one of these calculations, then I will give the full set of properties this matrices alpha and beta have to satisfy. So this is okay. Oh, let's do it. Now I have the Klein-Gordon product of this and this is delta KL. So I have alpha star EK alpha jk, and the product of this and this is minus delta KL minus beta star, because the Klein-Gordon product is antilinear with respect to the first argument. Here I get this star. Minus beta star ek beta jk. This has to be equal to delta ej. Okay. So if I transpose this matrix, this is alpha dagger minus beta dagger equal to the identity. This is a first condition for the canonicity of this transformation. So let me summarize the property here. I write u prime star equal the matrix alpha beta star alpha star u star. I suppress the indices, and the first condition I get is alpha dagger minus beta dagger equal 1. Okay. The second condition comes from asking that u prime star e uj equal 0 prime. Okay. So this is the second condition here. This condition here. And this gives, if you do the same calculation I did here, the condition alpha beta transposed minus beta alpha transposed equals 0. Do the calculation, you can verify this. Okay. Is there any question? Now I have these two relations. I can use those two relations to invert this matrix. This is a matrix which is block matrix made by matrices. Okay. So if I use this relation, I see I have alpha beta star, alpha star. If I put here alpha dagger minus beta dagger, this is the first relation, you see? And I put here minus beta transposed, alpha transposed. This is the second relation there. This is the inverse matrix. Because the first is alpha dagger minus beta dagger equal 1. And then I have minus alpha beta transposed plus beta alpha transpose equals 0. And the other two relations are the complex conjugate of this. Okay. So we get the inverse transformation here. U star equal alpha dagger minus beta transposed minus beta dagger alpha transposed u prime star. Okay. This is the transformation as is act on the modes. If you we get two more relations here by computing the inverse at the left. Put here the inverse to the left and the matrix itself to the right. We get two more relations which are important to be written. Because the inverse is unique, this has to be 1. So we get two more relations. One is, so minus, let's do for the second line, because one is the complex conjugate of the other. Minus beta dagger alpha plus, did I do something wrong? Plus alpha transposed beta star equal 0 and minus beta dagger beta plus alpha transposed alpha star equal 1. So these are the 4 relations that have to be satisfied by these matrices. Okay. We will see they all enter in the construction of the S matrix we are going to do. So if you revert the viewpoint, you can see how the canonical transformation act on the operators. Because now that you have, you write a duality relation. So if you write this the field expansion is the sum of UE E plus dagger E dagger, you can also write this sum of UE prime I prime, another creation annihilation operator, U prime star I dagger, and these have to be equal at the algebraic level. Okay. So what is the combination of the A that produces the A prime in such a way that these two relations, these two expansions are the same thing? It's just that you act by transposition. And let me write, for instance, the transformation of the operator A prime dagger equal to alpha star minus beta star minus beta alpha a dagger. Okay, this is the dual transformation to this. You can verify that this gives rise to this identity. You have to use, of course, the relationship to show this. Do this as an exercise. So before going on, let me make a comment. So as I said before, you arrive here at a writing of the two-point function which is closely related to this expansion of the commutator, but you can equivalent write the commutator. It is an identity. This is really an identity. In terms of the prime modes, this is also sum of u prime, u prime x, u prime star y minus u prime star x, u prime y. This and this are, this sum and this sum give the same function. The commutator is unique. But, of course, the 2-point functions are not the same. You can find a second quantization, which is related to the Bogoliubov transformation by asking that the vacuum is annihilated by the primes operator. And this is going to be sum of u prime x, u prime star y. This expression is not equivalent to this. It's something else. Okay? And also, now we are going to solve under which condition these two quantizations are equivalent or not. Okay? We are going to find the unitary operator passing from this to this. But I want you to draw your attention to another thing. The thing is that now write the expansion of this 2-point function in terms of the new modes. So this is going to be the sum in terms of the old modes. Alpha ij uj x plus beta ij uj star x plus alpha beta star ij uj y plus alpha star ij uj star y. This is the same thing than this. Okay. Now do the calculation. You are going to have a term which is. Let me write it in a rapid way. You get alpha star ux u star y. Allow me not to write the indices. And then you get plus beta star u star x u y. And then you get alpha beta star u x u y plus beta alpha star u star x u star y. Okay, there are 4 terms here. Now you can act with those rules, and you can show that this part here, the part containing u and u star is symmetric. Okay, this part is symmetric in the exchange of x and y. This part is not. If you compute the commutator, only these 2 terms are going to contribute to the commutator, and these 2 are not going to contribute to the commutator. So you can suppress those terms and get a third quantization. For instance, you can simply throw away these terms, and this is for you a third quantization. What you have done in doing this, you have thrown away the Bogoliubov transformation in favor of the Hopf deformation. What is the Hopf deformation? Let me tell you very shortly what it is. You know, you want to, our first lecture was to consider these commutation relations here. You see? And one practical way to implement those commutation relations, those come from physics, okay, is to use a pair creation annihilation operator, okay? And you may think that this is equivalent to this. Indeed, you are going to write Q as a plus a dagger over square root of 2, and p as a minus a dagger over square root of 2i. Okay? This is, you can check that if you make this definition with this commutation relation, you have realized this thing. But now you can deform these things this way. You can write here, introduce a second pair of creation annihilation operator and a parameter and the same rule you apply to P, you can verify that this also satisfies the commutation relation. So you can do this in terms not of one pair of annihilation, creation annihilation operator, but two pairs of creation annihilation operator. This thing is called a Hopf deformation rather than a Bogoliubov transformation, and it is related to the thermal aspect of the theory. So if you are going to suppress the symmetric part here, you still get a canonical quantization. Also, if you, what is it? I lost the book. You can just add something which is symmetric here and generalize the scheme of Bogoliubov transformation. Make a Bogoliubov transformation and then add a symmetric part which is arbitrary. Why I'm insisting on this point? Because now I am going to explain to you today, I hope, what is the standard way of understanding the Unruh effect. Okay? So let me summarize now before entering into the details what is going to happen. So you have the Minkowski space. You have a family of modes of the Minkowski space which is constructed in the standard way by using this Cauchy surface to play the game of canonical quantization. And then you are going to cover the Minkowski space with 4 patches. And now you are considering modes which are normalized only on this half surface. So if you want to make a Bogoliubov transformation between the standard modes and the Rindler modes, what you have to do is to complete those Rindler modes with a family of left modes, as you probably already heard. And then you play the game of Bogoliubov transformation, because this is a complete basis, and this is also a complete basis, okay? If you want to reconstruct the Whiteman vacuum in terms of the Rindler modes, you have to do this way. If you allow yourself only Bogoliubov transformation. But there is a little philosophical problem here. Suppose you are really living in this part of the universe and accelerating, or same thing if you are living in external region of the black hole. Okay, you are living here. You don't know there is something here. So why you should do this thing if you are a physicist? You should work with your tools which are located in this laboratory. But if you allow yourself this generalization of the Bogoliubov transformation with this symmetric term, I will show you as a final remark that you can really construct everything just in terms of the modes here. Normalize here, construct the more general quantization you can construct here, and then act with the translation group to reconstruct the thing. So Bogoliubov transformation is the standard tool, but it also has it has its own limitation. But now we're going to go further in this. So this is a for the moment, it's just a comment. When you construct the new vacuum, you can still have the freedom of adding here a symmetric term or to suppress this thing. What you are doing, you are destroying irreducibility. This is the point. Because this theory is also irreducible. This theory is not. But you allow yourself more possibility. Okay. So now we are going to try to see. So we have now, this is the schema of Bogoliubov transformation. We construct a Fock space of the A operators. And we construct a second Fock space of the A prime operator. Okay? These two Fock spaces. Question. As there exists a unitary transformation mapping one space into the other, or else, how can we implement this Bogoliubov transformation? The word implement means that we have a transformation at the algebraic level, and we look for a unitary operator realizing this concretely. What we look for so we are looking for a unitary transformation mapping the states, the prime states, into the non-prime states. So you go from F prime to F in such a way that U dagger A U equal A prime, or else we can write this A U equal A prime U, A U equal U A prime, and we know what it is. A prime is U alpha star alpha minus beta star a dagger. Here there are indices, of course. This is A, E, J, A, J, E, J, J. We have a family of such things. This is A, E. And the same for the dagger. U equals U minus beta A. I suppress the indices from now onward. Okay. So we want to construct the operator U. This will be the S matrix. Okay. So how do we construct this operator? We have to solve these equations. Okay. So this is the problem we want to solve in the following half an hour. So there is a technical tool which is also physically important in quantum mechanics, which is called the coherent states. Is this familiar to every one of you or not? Let me just remind you how they are defined. If you have just a pair of canonical operator, you can construct the n basis, where n is 1 over square root of n factorial a dagger n applied to the vacuum, or you can construct the coherent states. This is a complete basis. Means that the sum of n equals the identity. The coherent states, they are defined as the exponential of z is a complex number, a dagger applied to the vacuum. Okay, if you make an expansion of this is sum of Zn a dagger n over n factorial to the vacuum. So this is sum of Zn over square root of n factorial n. Okay. What is the important properties? What are the two fundamental properties of the states? The first is that they are eigenstates of the destruction operator. Okay. How do you prove this thing? Either you act with the function and you commute, or you use the Baker-Campbell-Hausdorff formula. So if you, for instance, use the Baker-Campbell-Hausdorff formula, a to the u a to the z a dagger, you commute it, and this is a to the z a dagger, a to the u a is the operator, eh? Times a function, a, u, z. U and z are complex numbers. This is Baker-Campbell-Hausdorff formula. Okay, so when you apply this to the vacuum, this to the vacuum is just the first term. This is z. So you get that a to the u a applied to z is a to the u z applied to z. In general, for any analytic function, f, no, I'm wrong, a to the u a, f of a applied to z is f of z, z. If f is analytic, you develop it in series, okay? On the other hand, I dagger z, this is easier. This is a dagger, a to the a dagger z to the vacuum. This is d to the z. You derive with respect to z this of z. Okay. A dagger z is d, the derivative. Okay. You are familiar with these things or not? Every one of you? Okay. So I don't need to be more to say more things than did I say. The only thing which is important is that to know this is an overcomplete set of states, and you integrate this over the measure and this is the identity. So we are going to insert this, yes?
Sorry, these are complete for the one particle system? Or?
This is for one particle, but then we put indices on the thing. This is just one particle. Then you have coherent states depending on indices. So this would be Zi. So there will be many complex variables around. So the point is that now we are going to transform this relation into differential equation because of this. So overcomplete because that here is not 0. Okay. I made a summary in my notes, which I will send you. Is there a question? Any question?
Yeah, so what do you mean it's overcomplete?
This is not 0. But this is a resolution of the identity.
Oh, I see. Sorry, yeah.
Is overcomplete. So they expand the identity as an integral, but they are not orthogonal to each other. Okay, these are the states which minimize the Heisenberg uncertainty relationship. So the rules you have to remember is that A applied to Z is Z applied to Z, and A dagger applied to Z is d over dz applied to Z, and the dual of this is A dagger applied to T is T star T, and A applied to T is d over dt star applied to T. Okay, these are the rules, and then you generalize these rules to analytic function of the operators. Okay. Now we are going to apply this here. Let me do it here so you can see it better. So we have two equations, operatorial equation, which are going to give to us the operator U. The operator, so we had, for one, at the beginning I put the indices also, and then I will not do it anymore. This is the first question. Okay, let's see how do we act with the coherent states. We bracket the equation in between coherent states. What is this? A acting on T is d over dt star T u z. Okay, and then we bracket this in between coherent states. So A acting on Z A acting on Z is Z, so we get alpha star Z T u Z, and I dagger acting on Z is d over dz minus beta star d over dz T u Z. Okay, this means obviously alpha star Ej Zj, and this is beta star Ej d over dzj. Okay, this is now a differential equation for T u Z, and a second differential equation comes from the other relation. This is T star T u Z equals minus beta Z T u Z plus alpha star d over dz T u Z. So we have to solve these two differential equations together. And we will see that to do it, it is crucial to have those properties there. Otherwise, we can't. This method is let me verify that I didn't write anything wrong. D over d star alpha star Z minus beta star T star minus beta Z alpha star? No alpha star. Okay. So it's a little bit tricky, but it's not difficult. This method works. This is a secret weapon. I mean, when you don't know what to do, bracket in coherent states your things, and maybe something comes out. So let's see how do we solve this. So you see the second equation contains only the derivative with respect to z. If we multiply by alpha to the -1, we get a differential equation. So then I comment why alpha should be invertible. Okay, so there are two things here that I've done. First, I have assumed that alpha is invertible. Is this true? You see from here this relation alpha alpha dagger equal to one plus beta beta dagger. Okay, if you take mean value of this operator in between a state, whatever it is, this is psi square plus beta dagger psi square. So you can never have at the zero eigenvalue this thing because of the presence of this term. And the same you can say for alpha dagger as the kernel, which is trivial, and the same with the second relation there, you show for alpha. So alpha and alpha dagger have a trivial kernel, so the matrix can be inverted because of this. So alpha dagger psi, the norm, it is always psi plus something else, never zero. So cannot be the zero eigenvalue there. Alpha is invertible. The second thing which is now which is important to integrate this equation is that this matrix has to be symmetric. So if this matrix is symmetric, I integrate it and then I show that the matrix is symmetric. So if the matrix is symmetric, this equation is easily integrated. So I get here TUZ is the exponential of Z alpha minus 1 T star plus, I forgot something here, a Z. I wrote Z plus 1/2 Z alpha minus 1 beta Z. Everything multiplied by a function of T star. Which is arbitrary for the moment, okay? This is true if the matrix alpha minus 1 beta is symmetric, otherwise this formula is false. Okay, because I acted here, so when I differentiate with respect to Z, this is going to give this only if the matrix is symmetric. Is it symmetric? We go back to our list of properties here. And we see we have this property, alpha. Let's do it here. The property alpha beta transposed equal beta alpha transposed. Okay, so let me compute alpha minus 1 beta transposed. This has to be equal to alpha minus 1 beta, okay? What is this? This is beta transposed alpha minus 1 transposed. Beta transposed I compute from here by multiplying by alpha minus 1. Beta transposed is alpha minus 1 beta alpha transposed. So this is alpha minus 1 beta alpha transposed alpha minus 1 transposed, and this is 1, so this is alpha minus 1 beta. So the matrix is symmetric. You see, we have used crucially this property. So this is the first step. This matrix is indeed symmetric, and we can integrate the first equation. Now we go into the second equation. So we have an ansatz for the solution, and we have to input in the other equation to see first if there is no incompatibility in between the two equations, and second how we determine f. Okay, let's do it. This is I would say this is the most important computation one does in quantum field theory in curved spacetime. It's the calculation of the S matrix. So let's do it completely. So put this inside here. You throw away this term because you know the value of this derivative here. You put this in here, and what you get is the following equation. We will get two things. One differential equation. So if you input this thing there, let's do it. You get Z. I write the thing and then we comment. F of T star plus df of T star. So I assume this form. I input it there equals to alpha star z f of T star minus beta star alpha minus 1 beta z f of T star minus beta star alpha minus 1 T star f of T star. This is the first equation where when we input the ansatz inside and we compute all the derivatives, okay? So you see that this equation, there are two things here. The function f depends only on T star. So the f of this term depends only on T star, and this term depends only on T star. This term depends only on z. So we have to equate this to this, and what remains has to be equal to 0. Otherwise, the two equations are incompatible. Okay? So the part which depends only on T star is this and this. So this is easily integrated. This is also a symmetric matrix. It's precisely the same argument than before. Then I can integrate the equation. So I get an equation which is df over dt star equals minus beta star alpha minus 1 T star f of T star, which means that f of T star is exponential minus 1/2 T star, or let's say 1/2 T star minus beta star alpha minus 1 T star. This is the solution. And the remaining part has to be equal to 0. This, where is it? So I get the sum of two terms, which have to be 0. So let me write it somewhere else. So first I write the solution. So the solution is this, the solution we found before. Where is it? F of t star, we have determined it, is minus 1/2 is plus 1/2 t star minus beta star alpha minus 1 t star. So apart from a constant, which is important, which we have to determine here, this is the solution. And then we have the compatibility equation, which amounts to proof. The compatibility equation reduces to alpha minus 1 transposed equal to alpha star minus beta star alpha minus 1 beta. This is also true. I don't give you here the details. It comes out from two relationships. This one, the last two relationships we wrote. This and this are equivalent to this. Prove it as an exercise. Okay. And this is, so we have solved the two equations. The two equations are compatible because of this relation. So it means because of these two relations, this makes the two equations compatible. And this is the solution for that equation. So we have found the matrix elements of the operator U between coherent states. So we can reconstruct the operator U now. And there are two last things we have to say. The first thing is that when you have a big ordered operator, we have this relation, T f of a dagger, big ordered, Z. This divided over Tz, because the states are not normalized to 1. This is f of Z and T star. Okay. Is it clear? Think of it. If you take, for instance, T, A, Z, what is this? This is Z, Tz. So Z is TAZ over Tz. Okay. And what it is Tz? So how do we pass from this relation to the operator? So the operator is going to be a big ordering. So is U, a constant that we have to determine, the big ordered exponential of the exponential where you find Z, you put A. Where you find T star, you put a dagger. So it's the exponential of A minus 1 minus 1. This is the 1 over Tz. This minus 1 that enters here, the identity matrix. Here there is no minus 1. Here you find in books the minus 1. Why? Because we have divided by the norm of Tz. Okay? A dagger plus 1/2 A Z A minus 1 beta A plus 1/2 A dagger minus B star A minus 1 A dagger. B-ordered. The B-ordered exponential means that you make the expansion and then you order all the terms by putting all the creation operator to the left. Okay? This is the solution. The only thing that remains to prove is what is this? What is this? When you compute now, when you apply this to the vacuum, okay, you get C squared. Because when you apply to the vacuum, all that remains is the identity. It is B-ordered. So C squared, the constant, is the crucial thing in a way. The fact that this constant is 0 or not means that the two quantizations that you have constructed this way are equivalent or not. They act inside the same Hilbert space or not. You see what I mean? So we have to compute this, and the fact that this constant is a divergent quantity on the denominator or not is the sign that what you have done is an implementable Bogoliubov transformation, means that the unitary operator exists or not. If you get a 0 here, the operator do not exist. Is it clear? What is this constant? So this I leave you for as an exercise. You compute this in the same way. So apply this to the vacuum. You will see that the thing that you have to compute is this. C squared. This is an exercise in coherent state calculation and Gaussian integrals. C squared is 0, U dagger 0. Remember that U maps the F prime space into the F space, and U dagger maps the F space into F prime space. So U dagger is applied to the vacuum, to the original vacuum. And if you use the expression that we have written, this is going to be 0 exponential 1/2 A alpha minus 1 beta A exponential. There's no more decordering because there is only A in this. Exponential of 1/2 a dagger alpha minus 1 beta a dagger 0. Okay. This is the quantity to be computed. More generally, you can show the following thing. You want to compute A, which is 0 exponential of 1/2 AMA. M is a symmetric matrix. Exponential 1/2 A dagger M star A dagger 0. This is determinant of 1 minus M star to the minus 1/2. This is the result. How do you prove it? Insert it here, a resolution of the identity in coherent states. And then you reduce this operatorial identity to Gaussian integrals. Because now A is going to act on Z. So you get here MZZ and here you get M Z star Z star. You integrate over the measure the Z star. This is going to be a Gaussian integral, and then you have to struggle a little bit with block matrices to see that the result you get is a determinant. Okay, this is done in, for instance, in the book of Blezo and Ripka. This way. I inspired my proof. The proof I presented here is in a way inspired by the methods of the first two chapters of this book. Many particle systems. Okay, so the normalization is the determinant of this matrix. 1 minus the determinant of this matrix. So let's elaborate this a little bit, and then we take a rest. So what is this constant? According to the formula you have to show as an exercise, I will send you the notes, all the details. This is going to be the determinant, so the matrix is, this is also our matrix M. So the constant square is the determinant, the matrix 1 minus A alpha minus 1 beta. This is the matrix M. Alpha minus 1 beta star. This is the matrix M star to the minus 1/2 according to the general formula. Okay, and now we act again with our identities. We know that alpha dagger A minus beta transposed beta star is the identity. This is one of the relations is this relation. It has to be satisfied by the Bogolyubov transformation. So we can recast this thing by multiplying. So here we do have this. So if we write this way, alpha dagger, we also have alpha dagger beta equal beta transpose alpha star. This is the second relation there, which means that beta transposed is alpha dagger beta alpha star to the minus 1. Okay? So, this thing, this identity, 1 minus equal to alpha dagger alpha minus beta transposed beta star. This is going to be alpha star alpha, and then we use this relation for beta transposed minus alpha dagger beta alpha star minus 1 beta star, which is precisely the thing we do have there. So 1 alpha Is this minus or plus? So this quantity here, I don't know why I get a minus now. We can replace this quantity, verify this as an exercise also, simply by alpha star alpha, alpha star alpha. So C square, because of this relation, now I'm just don't want to recollect it, but there is these two relations which are going to recast this thing just this way. So the C square constant is the determinant of the matrix alpha dagger alpha to the minus 1/2. Okay. So in the end, we have constructed the unitary operator implementing the Bogoliubov transformation. If we put here the constant, one of the determinant of alpha dagger alpha to the 1/4. This is the result which we are now going to apply to cosmological particle creation and to the Unruh effect. Let's take 10 minutes break. Other questions? So simply you have to redo the calculation now. There is nothing difficult in here. Once you know that the easiest way to do this calculation is to use coherent states. There are other calculations you can do, which to my impression are more complicated than this. But in the end, you get this result. And you see, condition for the existence of this transformation is that this determinant has to exist. And we will see immediately after the break that this, in the case in which you consider space-time, which is asymptotically Minkowski here and asymptotically Minkowski there, is going to be interpreted as the number of particles created. So the transformation is unitary implementable if you create a definite number of particles. It is not if this number of particles diverges. Okay. Yes. This relation, you have to multiply this relation by alpha minus 1 at the left and the right, and you get exactly that stuff. But I will send you the notes in which everything is done.
And they wrote also contribution from this stationary point is 1 over square root of b,
Yeah.
where b is the determinant of
Yeah.
something that you cannot compute.
Really?
Yeah, that's the point. For some,
I thought it was the Killing.
No.
So volume.
No, because it's not the volume, that's the point.
It's not really, it's the determinant of the Killing matrix. It's the equivalent of the.
No, but they write it in such.
Let's see whether it looks like
Yeah, that you think that it's V. Okay, they call it V, so you think it's volume.
No, but it's a determinant of the Killing matrix, right?
No, but it's not.
It's not. What is it?
Oh, it's very complicated formula. So this is the point.
It's not the Euclidean volume for sure. It's the flat limit of the Killing.
No, flat limit of the determinant of Killing matrix is volume. But it's not the volume, that's the point. So they wrote it V.
Yeah, well, it's not.
And I was always thinking it's volume,
Yeah.
but it's not. Yeah, and they write it, and it is the determinant of Hessian matrix. And this Hessian is so complicated.
So they haven't done.
Yeah. So everyone was thinking that it's like that. But it's not.
Very good. I'm going to check.
Because I also
I
have some in this paper which has some mistakes I need to replace. So don't download it. I will replace it in one page.
So what you prove is in the case of one simplex and two simplices glued together.
Yeah, that's because if you take one simplex, then you also can compute, but then you have one of the determinant of change of matrix from areas to line, some product.
Yeah.
But if you take the square of the
No, dovrebbero solo poterlo però non applicate.
So it's
so
a
it's
fancy way of
Io ormai non ho mai visto per unità
That's my English.
It's sort of square. You square it.
Yeah, it's the formula. And then it's written next in terms of
It is for the. And you get the other within 3D.
C'est la pratique que vous aviez déjà fait,
Non, on essaye comme ça.
Non. Si tu penses, si tu cherches à les décrypter dans les livres de Wald, c'est totalement incompréhensible.
Ah ouais.
À mon sens. Tu le regardes et qu'est-ce que c'est que ça? En fait, il y a ça. Ça, c'est le point vicieux. Cette chose, c'est la chose. Mais non. De faire tout de suite, de faire un coup qu'on trace sur le état de l'autre côté. Mais si tu veux, disons, chercher à les comprendre l'audience, c'est impossible. Pour moi. Je ne sais pas si vous l'avez voyagé ces deux. Non. Tu l'avais regardé pas?
Pas sur ce.
Is it true that if you take these equations for this matrix element and you put ansatz for this matrix element,
You put
ansatz,
the inverse?
ansatz. You write this matrix element as e to some s, then the equation for this s would be exactly the equation for generating function for a simplex transformation. Would be the same or not?
It is. I mean, the ansatz is you have to suppose it's quadratic. Then there are several possible derivations. Sure, it is the generation of the symplectic transformation.
Okay.
But I don't know of any simpler derivation.
Yeah, it was.
Do you know one derivation which is simpler? I would like to buy it. The other one I know are more complicated. This you really can integrate an exponential. The only thing you have to always keep in mind
this relation, but there are exactly the simplex.
Sure.
And then that's why it's integrated. So for CJ is the same.
Yeah, it's
the same.
But then square.
But then the point is that you have like integral over dl of delta LL. You can just skip this integration and then you have quantum relation. And if you want higher dimensions, you can do the same. You can do any higher dimensions, and you obtain the same formula. but no
I
one
mean,
can.
it's a formula with the volume. I mean, what is nice is that here you have integral over length.
Yeah. So that's why we computed it for a square.
The problem is that, yeah, precisely. But the problem is that, what is the problem? So how do you do more complex?
I don't know.
Because it's always easy to compute the square.
Yes.
Et Maïté, c'est combien pour 22?
Bah, faut que je revoie avec Mathéo et mais voilà s'ils sont bien ici, parce que vu qu'ils sont vu que Mathéo est pas là aujourd'hui.
Oh.
Mais normalement c'est bon, je ferai un email.
Tu envoies une confirmation?
Oui, mais avec c'était bon. C'est juste, je suis sûre que ça va.
Après, j'ai pas eu de suivi, alors en fait, on ne sait pas.
Ouais, ça m'aide. Je pensais que Mathéo serait là aujourd'hui, donc vu qu'il n'est pas là, j'espère qu'il a prévu de venir.
Je l'ai placé hier, hein, par contre.
Ah oui, là,
Il y a autre chose à faire.
Of course, it was surprised that it computed in one line.
No, I must say but I read this paper in your PhD, and yeah,
on the
on the 10-day symbol of pi.
It's
And then
getting
formula with one of
sketchy.
the square root of v, and I've always thought it was the v, the volume.
Volume, but it's not volume. It's V is the name for the determinant of pressure.
Which is impossible.
Ah.
Wait, I'm very surprised. I'm not surprised. Am I surprised? Because I think he denied option. The formula.
Okay, as far as I was checking all papers, it's everywhere they compute phase, and they may write that it's determinant of something, and that they have
Okay. So there's never a result to the asymptotic of the stain J involving the volume of the sequence.
as far as I know now. And it seems that it's not true. It's not true.
In fact, well, it's true for the square.
Oh no, it's like volume to 7.5 and some volumes at the tachygraph.
Right.
And also you have this determinant.
Yeah, your formula is horrible.
Yeah, it's also like
It's
change
nice
of
because
A
it
by
links.
L. And of course this change of areas to length sometimes it degenerates configurations and then it's evolving faster, so it cannot be in terms of time. So it's indirect proof, it cannot. Because there are some configurations not degenerate in which change of areas to length.
It goes up, but you take it as to account.
Yeah, so in our formula it's glowing. We don't know exactly how it's glowing, but we know that when you approach this region, it's glowing. It's like dominating. Unfortunately, I was really unhappy. No, he should be happy. It's based on his. It's like appendix to his paper. It's starting. Of course, he
doesn't. I don't think he minds in general.
No, mais
it's
là,
like the big. Yeah.
discussion.
No, I gave him this paper. He was happy.
Yeah, he's always, for Matteo and Valentin, that's the same. Basically, Matteo and Valentin said in their paper that he was completely wrong.
Yeah, no.
Or he was his statement was valid on the power council letter. His statement was valid only for very restricted cases. As long as he came first.
There are 2 persons lacking. They will come back, or they are destroyed by Bogolubo. By the way, on that blackboard, there is everything you need to do about Bogolubo transportation. Take a picture of it, and there is everything.
I'm gonna show it to my mom.
Carry it in the
By the way, you use it in quantum systems, no? Bogolubo.
Yeah, oh yeah.
Did you already know this?
I haven't seen it this way. I usually like.
You have an easiest derivation?
No.
Okay, just tell me if you know something, anything simpler. This is for me the simplest.
The exponential, of course, acts on everything to the right, right?
The exponential, decordering.
No. What do you mean when you wrote that? Something like exponential of
Everything is an exponential, of course. As I said, so let's start again.
What else would it be?
Sorry, exponential is here. This operator is exponentiated. It is exponentiated decorded. I mean, you take the powers, and in any power you recorder every term. This is the unitary operator implementing the Bogoliubov transformation. This is the definition of the Bogoliubov transformation. You see immediately that if you have a finite number of degrees of freedom, this operator always exists. But if you have an infinite number of degrees of freedom, the crucial thing is if this determinant is convergent or not. Okay? A Bogoliubov transformation is non-trivial if the beta matrix is non-trivial. This means that we are mixing creation and annihilation operators. If you just have the alpha matrix, the Bogoliubov transformation is not doing anything. It's just reshuffling the modes. Okay. So let's apply this formula to the first case of cosmological particle creation. So you have here a space-time which is somewhere curved inside here, but which is asymptotically Minkowski here and here. So you have your field entering here and scattered by the geometry, okay? And this operator here is going to be interpreted as the S matrix. So you have 2 sets so you have a state psi here, a Wolf state, that is going to go to something which you can call psi in here. And here you have a set of operators A in and A dagger in. And to evolve in psi out there. And you have the creation annihilation operator out. So in and out. And the S matrix relates the state in and out this way. It's of course a unitary operator, as you all know, but it exists or not depending on the existence or not of the thing. So how are we going to interpret this determinant? Because of this relation, the fact that the determinant exists is the same that the existence of the trace of beta star beta, okay? And how do you interpret the trace of beta star beta? If you think of the S matrix there as relating the out operators to the in operators, you write everything here in terms of the in operators, and this is the S matrix, provided the same thing exists. So if you are going to compute the mean value of the out number operator, this is the number operator of the E species of particles, and then you apply let's say this, and then you apply this transformation rule here, you see that this is precisely the trace. This is because of this beta star beta here. This is the trace of beta star if you sum. So the S matrix exists if you create a finite number of particles. Otherwise, this determinant is infinite because the trace is infinite and the operator does not exist.
The subscripts on the operators there are...
This is the number operator.
Yeah.
Out.
Yeah.
Out. Then you input here the transformation, and you see that you are going indeed to compute the trace of this. Okay. So this is a proof of what you can see written in the book by Wald or in the book by Biller and Davis, depending of the fact that you have created by the expansion a finite number of particles or not, the S matrix exists or not. Okay? Is there anything non-clear?
So like whenever they do this, they look at like the far past and the far future, and they don't talk about like any intermediate state. Is there some way to do like a Bogoliubov transformation to some like finite time or like in the middle of the expansion?
I mean, you don't know the concrete expression from these things, but because of the Klein-Gordon stuff that was written there, if you use the states at an intermediate step and you push backward your Cauchy surface, then you end up with the free states here. What do you mean?
So I just mean like you.
The S matrix is by definition an operator that maps out states into the in states, but of course passing in between. But they do not map. You cannot write a concrete expression for this, but you don't need it. What is the question, by the way?
Yeah, no, you got answers.
No, I'm not sure.
He was asking if you could stop, if you could stop somewhere in the middle.
I mean, in principle, you can define what you want. The point is that why the S matrix is useful, because it speaks to us of free fields. So the very notion you are using of particles, let's say, are asymptotics one. Here you don't know what kind of mess there is inside here, but you don't need to know it. But from the viewpoint of the Klein-Gordon structure we have been describing, if you know that here the situation is non-free curved, but you can push this Cauchy surface back in the past, here your state, which is complicated, is going to go in some free Minkowski state. So the normalization computed here on the normalization computed there is the same, because it's independent from the Cauchy surface, from the choice of Cauchy surface. This is the global hyperbolicity hypothesis. The concrete expression of this this wave function psi, you don't know it. Okay, but you don't need it. To relate the notion of particles is an asymptotic one. Okay. Is there anything non-clear? So this is the first standard application to this formalism. You have a quantum field theory evolving on a manifold which is locally deformed, but is asymptotically flat, or even is asymptotically flat in one direction. You can use the direction in which is flat to do your Klein-Gordon normalization and everything, and then let the system evolve. If you end up in another asymptotically flat situation, you build the NS matrix this way. Okay, it exists, provide this thing exists. The second, so now we have done a use of the Bogoliubov transformation this way. In the Unruh effect, now we are going to relate the modes built here and here with the standard positive frequency modes of the Whiteman vacuum in the same way, actually. Okay, so let's start. We won't finish today. We will finish on Monday this Unruh thing, and do also the black hole on Monday, which is more or less similar, of course. So we start again with the description of what, geometrical description of what we are going to do. We had already a first derivation of the Unruh temperature by the Unruh-de Witt observer the other day. You remember? We computed what an accelerating observer sees modeling the detector the way we did. Okay? And it sees a temperature which is proportional to acceleration. So the accelerating trajectory was given by parametrization using its proper time this way. This was the parametrization of the accelerating trajectory. Okay. So Rindler's idea was to study the geometry of this region, which is called a wedge, by extending this coordinate system to the whole wedge. So we built a coordinate system and there are two other spectators, which are the transverse variables. This covers this part of the Minkowski space. Okay. This part of the Minkowski space, which we can call the R region. I'm doing this description in a little bit in some detail, because when we do the black hole, it's more or less the same thing. Okay. We are covering this region of the Minkowski space with this set of coordinates. This set of coordinates is, of course, an orthogonal coordinate system. If you compute the metric, let me not write for the time being the x and y part. This is going to be psi square eta square minus the psi square. So there are no mixed terms. It's an orthogonal coordinate system. So these curves are mutually orthogonal in the Lorentz sense, of course, at every point. also, it is of the highest importance to pass to the light cone coordinates. U is t minus z. What is t minus z? Is minus psi exponential of eta, of minus eta. Minus exponential of minus psi or minus eta plus log psi minus exponential of minus u, where u is eta minus log psi. Okay. You can call this log psi star, which is going to be the analogous of the tortoise coordinates in the black hole. And if you use that coordinates, you get a metric which is conformal to the Minkowski metric. Okay, so this is, let me, okay. If you introduce the other one, this is e to the eta plus log psi, e to the v. And you see that in this region, u is negative and v is positive. Let me put it here, a summary. In region R, the right wedge, u is e to the minus e to the minus u equals minus e to the minus eta plus log xi, and v equal e to the u equal e to the eta plus log xi. Eta is the Rindler time. This is a curve in which psi is constant, and it is we need to compute eta this way, so we got minus eta plus log psi is minus log of minus u, and eta plus log psi is log v, in such a way that eta, the Rindler time, is 1/2 of log v minus log of minus u. This formula has to be kept in mind when we are going to compute the Bogoliubov transformations relating the Minkowski and the Rindler's mode. Okay. Now, if you are a Rindler physicist and you live in this world, in this right world, you can look at the world with the eyes of a Rindler physicist. So, suppose you are looking at this thing, which is traveling this way in the Minkowski spacetime. Okay? So it has a constant z. If you look at it from the viewpoint of the Rindler world, this is psi. We can call psi 0, this constant. Psi cos eta. So psi of eta is a constant over cos eta. So this thing is looked from the Rindler observers as popping out from the floor at eta equal minus infinity, then going up to maximal 8, and then going down and disappear below the floor at eta equal plus infinity. Okay? This is what happens to this thing. But if you are going to compute the proper time the whole process has taken, so this is the integral, you use that formula with this, you input this there, you get that this proper time is 2 psi 0. Okay? Took the s square, the integral from minus infinity to plus infinity of here we have psi 0 over cos square minus d psi is this psi 0 square s hash square over c hash to the 4 eta. So this is psi 0 square over c hash 4 eta. So this is the integral of psi 0 d eta over c hash eta square, which is psi 0 hyperbolic tangent of eta from minus infinity to plus infinity, which is 2 psi 0. So even if you are a Rindler physicist, and even if you see the thing emerging from the floor and getting into the floor, the gravity, you see the gravity of the floor so strong that even light cannot escape from it, you know that it takes a finite proper time to do this. So there should be life under the floor. So you see this region you can see from here, and you understand that there is another horizon here, so that your world is not complete. You have to complete it here, and in the end, if there is something here that does not come from here, it has to come from somewhere else. So this is just a heuristic way of saying that even if you don't see this region, just making experience here, you can suspect that there is something else in your universe. And indeed, if you are thinking in terms of this u and v variables, you can easily understand that you are going to prolongate these u and v variables to positive u and v here, positive u and negative v here, and negative u and v here. Okay? You can do it by hand, but let's say the more interesting way to do it is to think of this coordinate system, which at the very beginning is describing only the Rindler wedge. Okay? Think of it as describing the complex Rindler wedge. What does it mean? That now you consider psi and eta as complex variables. Okay. This is standard thing you do always in quantum field theory. Indeed, I don't think we can do anything else except from Bogoliubov transformation. There is this plethora of possibilities, but you always look for analyticity properties. Here I'm talking about the geometry, but the analyticity properties of the geometry are always reflected into analyticity properties of the correlation functions. Okay? The physically important correlation functions we construct, they are always identified by their analyticity properties. Okay? So let's do this prolongation. So if we write t equal psi plus ez, hyperbolic sine of eta plus e rho, and z equal psi plus cz, hyperbolic cosine of eta plus e rho, we know already that if z and rho are 0, we are in the original Rindler wedge. It is identified by zeta equals 0, the imaginary part of this equals 0, and the imaginary part of the angle equals 0. Okay? If we now, for instance, consider now, for instance, rho equal minus EP over 2 and psi equals 0. This is another real sheet of this manifold. What it is? This is IZ. S hash of eta plus E minus EP over 2. This is minus I cos eta. Minus I cos eta times I. This is Z cos eta. And this is Z sinh eta. So we are describing, this is the first part. Now we are here. Of course, if you write the metric ds in these coordinates, now eta is a space-like coordinate, and zeta is a time-like coordinate. So the metric is now zeta square minus zeta square d eta square. And this is, you know, is the Milne cosmological model. You see, the metric is not static in this region. It depends on time, and zeta is now a time variable. Okay? Now, if you compute u and v here, you see that both u and v, defined as before, are positive in this region. And now we go to the important region, which is L. L is another real sheet of this manifold obtained just putting here rho equal to pi. If rho is pi, I'm changing the sign of the thing. S hash of eta plus E pi is minus S hash eta. C hash eta plus E pi is minus C hash eta, means that you take, if you take, this is an extremely important observation now, is going on here. Take zeta equal 0 and rho equal minus E pi, let's say. Okay? The coordinate system becomes t minus psi s hash eta z minus psi c hash eta. This means that in this region, the time that goes this way here goes in the opposite sense. So what is positive frequency in the right wedge will be negative frequency in the left wedge. This is the source of the Unruh effect. Okay? So we need to write here the analogous formula of this. So t minus z which is u, now going to be minus psi a to the minus eta, means a to the minus eta plus log psi, so that eta equals minus eta plus log psi equals log u. Remember, u is positive here, and u t plus zeta v t plus zeta. This is minus psi e to the eta minus psi minus e to the eta plus log psi, so that eta plus log psi is log minus log of minus v. So that here in the, this is in the left, in the right wedge, and in the left wedge we had eta equal 1/2 of log u minus log minus v. Minus log u, no, there is a minus here lacking. Right? Why I'm concentrating on this thing? Because to compute, is there any mistake? You can correct it, if any. Because what is the point? Now we are going to do the quantization. We will start it today and end on the next lecture. I don't want to cancel this. Remember that if you now let's do a step back. When you write the positive frequency modes in Minkowski space, the standard ones, you get a minus here, and this is the positive frequency mode. What does it mean, positive frequency? That if you compute E d over dt of this mode, this has a positive frequency, omega. Okay? These are the standard modes. What is the analyticity of this mode? As I told you the last time, if you can, this is a real point on the real manifold, but you can extend this to the whole backward tube. You can put an imaginary part, so write it this way, e to the minus ikx, this is the Lorentzian product. You can write here a z, where imaginary of z is a vector in the backward tube, in the backward cone. In particular, if you want simplified presentation, you simply say that you can put a time which is complexified with imaginary time negative. But it's more than this. It's a huge domain on analyticity, and the whole domain is important, by the way. So you get this property, the fact that this wave is decreasing when you put an imaginary part to this time in such a way that this minus sign plus the minus sign which is here makes something which is decreasing. So this is the reason of having this analyticity property is going to be translated into what happens to the analyticity properties in the variables u and v. And this, you can easily understand, that property is equivalent to having everywhere imaginary of u negative and imaginary of v negative. This is the spectral condition of the standard Minkowski quantum field theory expressed in light cone variables. Okay? So when we are going to make an analytic continuation of the modes, which are defined and normalized here to this region, you are going to do it by keeping this analyticity property. And this will provide the weights of the Bogoliubov transformation. Okay? It's just this. So let me start to write the Klein-Gordon equation, and then we will finish the thing next week, just to start with. So we get a little bit advanced. We are going now to solve the Klein-Gordon equation in the wedge, in this region. And we are going to use this surface, which is half of a Wool-Cauchy surface, to normalize the modes. Just this part. So this is a global hyperbolic manifold in itself, this wedge. If you give Cauchy data on this surface, you determine the Wool solution here. You cannot determine the solution here uniquely, but you determine the Wool solution here. Okay, so you can do quantum field theory in this wedge just using this. Then we do this analytic continuation, and then we do the Bogoliubov transformation. And then we take a trace, and we get the standard interpretation of the Unruh effect. But then I will show you how to do just using this mode and forgetting about this. This will be the very end of the next section. So just to start with, if we write, so the geometry is this. So if we use the standard formula for the Klein-Gordon operator, the square root of the determinant of the metric is just psi. So this is when you do the time derivative, you get 1 over psi d eta. Then you get psi, but the inverse is 1 over psi square. So you get 1 over psi d eta phi. And then you get here, this is 1, so 1 over psi d psi, psi d psi phi. Then the rest is trivial. Minus dx square minus dy square phi plus m square phi equals 0. This is the Klein-Gordon equation in the Rindler wedge. So psi does not depend on eta. You can take it out, multiply everything by psi square. So this is going to be d eta square phi minus psi d psi d psi phi minus xi square dx square plus dy square minus m square phi equals 0. Okay. And now you make a positive frequency ansatz. You say that the modes is positive frequency with respect to the Rindler time. So you are using the natural notion of particles for the Rindler times. Positive frequency in the flat space means A e omega t. Positive frequency here means A minus e omega eta. Eta is the Rindler time. Then you get this part which is trivial. So you suppose that this also is ekx plus ekyy. And then you multiply by a function to be determined of xi. Okay? This is the ansatz you do for the modes. Of course, in the end, you have to verify that when you normalize with respect to this Cauchy surface, you are going to get a complete set of modes in the wedge. So if you apply this, here you get minus omega square. So minus omega square, we are going to put the minus omega square there. We get xi dxi, xi dxi f plus omega square minus xi square kx square plus ky square plus m square f k omega psi equals 0. Okay, all right. So this is now just an equation, a differential equation, ordinary differential equation in the xi variable. This is very well known, is Bessel differential equation, whose solution, which is normalizable at infinity, is the so-called Macdonald function. This is the index. You normally have a minus sign here in the Bessel equation. Since there is a plus sign here, you get I omega is the index. Then you have this coefficient entering as a multiplicative coefficient here of the psi variable. Okay? So in the end, the ansatz that remains to be verified is that the modes u, which depend on k and on omega, are written this way, apart from a normalization, a to the minus e omega eta, they are positive frequency with respect to the eta time, plus ekx, I'm summarizing x and y in this notation, times k of I omega, let's call u the square root of everything, psi. These are the positive frequency modes. And then you have to normalize them. You normalize them by using this Cauchy surface. So what are the rules? You have to compute this thing. uk omega, uk prime, omega prime. This is going to be I times the integral over this surface, sigma, eta equals 0, let's say. The induced measure is dxi dxc dy, is the Lebesgue measure with no weight. And the normalized time derivative is 1 over xi d over d eta. Verify the things I'm telling. So you put here 1 over xi d d eta u star k omega u k prime omega prime and compute. You will see that this is going to be delta of omega minus omega prime, delta of k minus k prime, times a normalization, which you have to compute as an exercise. This is going to be an exercise in the theory of Bessel functions. Okay. In any case, even if you don't, even if you don't compute this normalization, this is irrelevant because this normalization is going to disappear at the end of the calculation. Okay. Now the point is that we want to compare these modes with the standard exponentials. Okay. We cannot do this directly if we don't before say what we put in this region. Okay. Doing this is just an exercise in computing the analytic continuation of just this part from this region to that region, always keeping imaginary of u negative and imaginary of v negative. If we do this, we are keeping the same analyticity properties of this. So the beta, in a way, we are doing a trivial, in a trivial way, implementing the Bogoliubov transformation. Yes?
Sorry, you said that kx squared plus ky squared plus n squared is n?
Is u, what? U. I call this u. In any case, the measure, you see, the measure here is xi over xi. So it's a scale invariant. You can even forget about this when you do the calculation. So we will do this exercise because it takes a little bit of time and compute the Bogoliubov transformation on Monday. So we will finish with the Unruh effect because we will see that if we do this and we compute the trace over the left modes, we get a thermal distribution. So this is a complete calculation of the Unruh effect. And in the same vein, we will do Hawking radiation on Monday. And then on Wednesday, I will tell you about these spacetimes which are not asymptotically Minkowski, nowhere, like de Sitter or anti-de Sitter. And that will be the last lecture. Okay. Is there any question? No? I will send you the notes with the whole calculation of the S matrix. By the way, that blackboard is more or less everything you need to know about Bogoliubov transformation. If you want, I can tell you more, yes. I make an example. I will discuss this. We want to discuss now? We may. In private. Or I can make a little bit appendix at the end of this calculation.
No, you mentioned it's just a generalization. So a Hopf deformation is when you have two?
You have an algebra and you make two. You make a product and a coproduct. It's a mathematical construct which is important in the theory of quantum groups. But here it's important because its relation with thermal quantum field theory. Because of, thermal field theory is made by doubling the degrees of freedom. But we will see appearing here the Hopf deformation. When we take the trace, it's exactly the same thing.